Hello everyone, welcome to another video. In this video we actually are starting a new series. We're going to be talking about programming bare metal programming on a Raspberry Pi 4. So this should be exciting. I'm going to assume that you don't know a whole lot about assembly, so we're going to even start from the beginning with that as well. I always found it interesting when you do a tutorial and you want to get started on something and they assume that you already know how to do the things in the tutorial, and it's like, why would I watch the tutorial if I already know how to do this? So we're going to start out pretty basic, and we're going to move forward from there. The project goal will be to blink an LED on and off. That will be in a future video. We don't want like a 4-hour video or whatever it'll take to get there, so we will break this into a multiple series of videos, thus a tutorial series. So some equipment that you will need is a Raspberry Pi 4. And yes, it is a Raspberry Pi 4. If you have a 5, this might work because the chipsets are similar. This will not work on a 3, a 2, or a 1, or a compute module, or any of the other ones. So when you get into assembly, it's very specific to the chip that you're programming on, and the Raspberry Pi 4 is the chip that we are going to be targeting. Specifically, it's the BCM 2711, but we'll get there. Anyway, so to get an LED in this future video to work, we will need a resistor. I chose a 5 kilo ohm resistor. Why that specific resistance? It's the first one I pulled out of the box of resistors, so I went with it. You will want a resistor. You will want to limit the amount of current. You don't want to really create like a short circuit. That could be bad for your Raspberry Pi. If you were to short it out, it might not work anymore. So, resistor. You definitely want a resistor. You probably could get by easily with like a 1 kilo ohm. I think those are probably one of the most common ones. It's just that your LED will burn a little bit brighter. Obviously, you'll also need an LED. I have a little breadboard. You'll need some wires to hook all of this together. A computer to develop on. I am going to be using Linux Mint, which is derived from Ubuntu, which is derived from Debian. So that is what you will see on your screen. This will also work with Windows. So if you're on Windows, don't worry, you can still do all of these things. The process might just be slightly different for like the way that the file explorer looks on Windows will look different than what it looks like on my machine, and also the assembler will have .exe on the end of it and things like that. It's small little changes here and there, but overall I've tried to make this as neutral as possible. You'll need a micro SD card because the Raspberry Pi needs that to run. So, yep, you'll need one of those, and you'll need means to write to it. Now, you can get a little micro SD to USB. I actually grabbed one of these. They're fairly cheap. They work well from what I have experienced. Also, your computer might just have a built-in card reader, and if it does, use that. Go for it. Also, we will want to test our Raspberry Pi to make sure it's working. If you just want to assume it works, I suppose you could, and it will save you from having to get a converter from the mini HDMI to the full size. But I would recommend that you test it, just because if something isn't working, it rules out that your Raspberry Pi is not dead on arrival if you just ordered it, or dead from sitting in a closet, or who knows what. So one of those. Now, for software, we will be using Raspberry Pi OS to test our Raspberry Pi to make sure it works. You can go to Raspberry Pi's website, and under the software section, they talk about their fancy little imaging program. Boy, does this make things very easy. I remember the first generation was not anything like this, so this is super handy. You just pick that you have a Raspberry Pi 4, we will be doing 64-bit programming, so we will test with 64-bit operating system, and then you specify your storage device, hit next a couple times, and it will put Raspberry Pi OS on your SD card, and then you can test your Raspberry Pi. So to test our Raspberry Pi 4, let's step over briefly into real life. Your Raspberry Pi 4 will come in a little box like this. And when you open it up, you will see your Raspberry Pi. Exciting stuff. Now, if I take it out of here, you can see that it has these mini little HDMI ports. I don't really have a monitor that supports that, so I had to get this converter, which will convert it from the HDMI mini to the full size. You might have to do the same thing unless you have a monitor that supports that for some reason. And then, as I mentioned before, another tool I used was this USB to SD card reader writer. You just stick the SD card into that little slot, and it allows you to read it just like it's a flash drive. After that, this will all be flashed and ready to go. So you can see that I have it hooked up here. When you actually plug it in, it will come to life, and these little lights will start flashing. This camera's not focusing to save its life, but anyway, this rainbow screen will appear. That means that the graphics card has loaded up, and then it will start loading Raspberry Pi OS. Once it does that, you'll see that it shows the logo, and then it will fly through in the bottom left-hand corner all the different Linux stuff. The screen will briefly go black after that, and eventually a mouse cursor will appear, showing that everything kind of loaded up, and you'll be greeted to the welcome screen. Now, we won't actually be using Raspberry Pi OS, but this shows you that your Raspberry Pi indeed is working. Alright, so your Raspberry Pi is working. Now, the next software application that we will be using is FASMarm. If you followed along with my x86 BIOS assembly tutorial series, you'll know that we used FASM there as well. So why not stop using a good thing, and we'll continue using that. Now, there are some caveats. You can see from FASMarm's website that it is for Windows and Linux, which is handy for the target audience. However, you'll notice that it does not mention Apple in there. I am assuming it might be possible to compile it from source, because they do have source code, to make it work on Apple. However, that is outside of the scope of this series. So if you want to program on Apple, you'll have to find a different assembler and probably use the GNU toolchain, I'm guessing. That's the official one, I think, that even the ARM website talks about. So you can use that one. Benefits of FASM over the GNU toolchain is to make an LED light just turn on with FASM is, I think, 74 bytes, something like that. And with the GNU toolchain, after you create an ELF package and then convert it to binary and flatten it all out, or whatever the steps are. I haven't done it in a while, so I don't remember all the steps. I have tried it. It makes a 1 kilobyte file. So these are like a tenth of the size. So that's one benefit. Another benefit is it has a really powerful macro language. So we will be taking advantage of that as well. Obviously, if you want to switch in the future to using GNU, then the macros will have to be rewritten in a way that that assembler understands. And so there's that. The other caveat that we'll have is this is an assembler only, and the series is only going to be covering assembly. So it will not support code in C. Again, if you want to do C programming, this is not the tutorial series that you're looking for. It's going to be focused solely on assembly. Um, and if you want to include C in the future, you'll have to switch to a tool chain that supports C. All right, so I think we've covered all the caveats. There are definitely advantages to using FASM. Um, it's really lightweight. It makes tiny little programs. Works great. But if you want to do C programming, that's outside of the scope of the project. It's only for assembly. And so, yeah, you've been warned. Let's look at the other software you'll need. Visual Studio Code. Yes. So their website's changed. I've noticed that. I haven't been here in a while, but I remember when it was all black and everything was colored text on top of a black background, and now we've gone to a light background. So I'm guessing the light theme is the new dark theme? I don't know. Anyway, you will want to download it for your operating system. Mine is derived off of Debian and Ubuntu, so I'd have to download the deb file. I already have it installed, as you can tell, because the agenda is written in it. If you're on Windows, it is smart enough to know that you're on Windows, and you can just download the Windows installer. Inside Visual Studio, I also recommend getting an ARM assembly syntax support some way or another through an extension. I will be using this one written by, it looks like, Dan C. Underwood. So it seems like it works well for what I'm working with, and if you want your text to not just be all white, you probably will want a syntax highlighter of some sort. And that takes us to our topics. So why Raspberry Pi 4? As I mentioned, the 5 is out, and the 5 is faster from my understanding. It has more RAM, and it has an off switch. That's a nice little convenience thing. You don't have to just unplug it. So why would you want Raspberry Pi 4? Well, main reason is cost in our case. A Raspberry Pi 4, when I bought mine, was $35. A Raspberry Pi 5 was like $120 or something. We're going to be writing tiny little programs that move really, really fast. We don't necessarily need a super fast processor. We don't need tons and tons of RAM. It's overkill for what our project is, and it's cheaper to get a Raspberry Pi 4. So hopefully it'll be more accessible to people to work with. Why FASM? Well, we already actually touched on this. FASM makes really small binary files. It has awesome macro support. Its preprocessor is, I love it. It's great. So we have that. Also, if you're following along from the BIOS tutorial series, you're already kind of familiar with it. So familiarity is always a nice thing when you're working with a tool. So we're going to move forward with that. And also, like I said, it's assembly only, not C compatible. All right. And we've already actually talked about flashing Raspberry Pi OS onto your Raspberry Pi. So we've covered a few of these things. So let's dive into the code now. I'm going to just make a boot.s file. And you might be wondering why .s and not ASM. I would prefer ASM. However, I always have to keep overriding and telling it that the file I'm working with is ARM, and by default it's picking that it's a PIC18 file, which is an extension I have, so it must steal that extension means that. Anyway, to make it easy and not have to constantly switch over to ARM, I'm using .s. So we're going to be looking at just 3 lines of code today. U64 is the first line that we'll be looking at. What this means is that we are about to write a 64-bit program. If you don't know what that means, we'll talk about that in just a little bit. Next, our processor is 64-bit, as we talked about. ARM version 8. Another little tidbit about the processor. Helps if you spell it right as well. And the last one we will talk about today is our origin point is at hexadecimal 80,000. So let's pull up a little bit of the specifications first to try to keep this easy. Here is from Raspberry Pi's official website, their technical specifications. And we can see that we are using a BCM 2711. If you don't know what that means, don't worry, we'll cover that. The ARM processor is a Cortex A72. Again, you don't really have to worry about that quite yet. ARM version 8. Oh, this actually is applicable to what we just did. You can see that we are using ARM version 8. So very good. And also it says that it's 64-bit, which corresponds to us using 64-bit and that our CPU supports 64-bit. So the first things you might be wondering is, what does 64-bit even mean? What is this number? Why is there an X in it? I mentioned the word hexadecimal. What does all this mean? Well, if you were looking ahead under topics, we're going to be covering the numbering systems. The numbering system that you generally use is decimal. I'm assuming if you're anywhere in the Western world, and I think even the Eastern world uses decimal now as well. So just bear with me. I'm going to start out extremely basic, and then we're going to build from there. Decimal is base 10, thus the deci part in decimal. It is base 10. Anyway, to start out, extremely simple, we have this little circle, and this circle means the number 0. And now we have a vertical line, and this vertical line represents the number 1. Then for number 2, we have this little snake-looking character that kind of is slithered up on your screen, and you know what the rest of the numbers are. Why on earth did I do that? Well, to prove a point. And that point will be in just a few numbers from now. So 6, 7, 8, 9. All right. So what little character represents the number 10 in decimal? It's not a circle, it's not a vertical line, it's not a little snake thing, it's not this little trident, three-pronged thing. There is no character to represent the number 10. The number 10 is represented by 2 characters. In this case, it's the character 1 followed by the character 0. Okay, so you're thinking, I know that. I know how to count to 10. That's wonderful, because we are going to extend the knowledge now to hexadecimal. So this was decimal, hexadecimal. Hexadecimal is base 16. And actually, I'm going to write it this way rather than this, because we're going to avoid some confusion, I think. So counting is identical from 0 through 9 in hexadecimal. Now, in base 10, 1, 0 represents 10. In base 16, 1, 0 represents 16. So how do we get between 9 and 16? Well, what we need is we need symbols to represent the numbers 10 through 15. The symbols that we have decided to use, we have stolen from the alphabet, and we use the letters A through F to represent these numbers. Yeah, brain thinks in decimal, definitely. Okay, E is 14 and F is 15. Okay, now the way that these are actually represented is we put a 0 and an X in front of them. And that's why there's an X here. So when it says 80,000, it is actually referring to a hexadecimal number, which is off of base 16 rather than base 10. And we'll talk about why we use hexadecimal in this way in just a little bit. Now, if you are coming from a 32-bit programming series, 80,000 is not the number you're used to seeing. You're used to seeing 8,000. So the way this works is when you write a program, it is placed by the bootloader at a specific RAM address. Now, the way I've talked about RAM before is like a locker room at the gym, where you can store something in each locker, and when you have lockers, they have numbers on them, usually starting from the number 1 up to however many that they have. And in the same way, the RAM addresses each have a number associated with them that point to where they are. Now, for our program to work properly, it needs to know where the bootloader has stuck our program. Did it stick it at address 0? Well, that's what it assumes. It assumes 0. So we have to put in an origin point and tell the assembler, actually, our program is going to be stuck at RAM address 80,000 hexadecimal. So that explains this number. Let's get into binary now. Binary is base 2. And again, we have 0 and we have 1, but we know that 1, 0 has to equal whatever the base is. And the base in this case is 2. So 1, 0 equals 2. Now, some numbering conventions allow you to do this, which I think is handy. However, from what I've seen, ARM does not necessarily support this format. So I will use it in this tutorial on how to count and why binary numbers are important and why we're using them in the first place, but we won't be able to actually use them that way in code. And if you know a way around that, let me know, because that'd be wonderful, I think, in a lot of cases. All right, so we have 0, we have 1, and then this is 2. You might be thinking, well, how do we get to 3? Well, let's go back to the system we're most familiar with. So when you get to 10, if you want to go beyond these 2, like the number 11, what you do is you increase the ones place, which there you have the ones place, the tens place, and then if you have a number like, oh yeah, we'll do that number. So you have your ones place, your tens place, your hundreds place, and your thousands place. Similarly, in binary, you have multiple places, and to get to the number 3, you would put a 1 in the ones place. Now let's look at something that you might not have known about the numbering system that you use. 10, which is the base of the system in decimal, to the 0th power equals 1. 10 to the first power equals 10, because it's 10 by itself. 10 to the second power, so 10 times 10 equals 100. And 10 to the third power equals 1,000. So if you were to take and find another way to represent this number, you could say it is equivalent to, oh boy, this is going to look complicated, but it's not, don't worry. 9 times 10 to the third power plus 9 times 10 to the second power plus 9 times 10 to the first power plus 9 times 10 to the 0th power. Now this might look really confusing, but all it means is this. We're taking 10 to the third power is 1,000. 9 times 1,000 is 9,000. 10 to the second power is 100. 9 times 100 is 900. 10 to the first power is 10. 9 times 10 is 90. 9 times 10 to the 0th power, well, this is 1, so 9 times 1 is 9. If you add all those together, you get 9,999. You might be thinking, why did we just go through a super complicated way to write out numbers that are very easy to write? Well, the reason is, let's go to binary. This is base 2. So if we use 2 to the 0th power, again we have 1. 2 to the first power is 2. 2 to the second power is 4. And you're going to see that they just keep doubling. And that's the way binary works, is 1, 2, 4, 8. 8 times 2 is going to give us, brain thinking ahead, 16. And if we did 2 to the 5th power, we would have 16 times 2, which is 32, so on and so forth. Now, let's say we want to break down this number, 3 ones. What would this be? Well, you can count like we were doing here, and you can figure out that, well, there's 2 ones here, so just like 99 in decimal has to go to 100, because there's no symbol after 9 in that numbering system. We're at 1, we're at the max, so we overflow to 100. This must be the number 4. And indeed, if we look at this with 0, 1, 2, 2 to the second power is 4. So these are the names of the places. You have the 1's place, the 2's place, 4, 8, 16, 32, so on and so forth. So let's understand this number. Well, we're going to break it down. Starting from left to right, 1 times 2 to the second power, because remember this is 0, so 0, 1, 2, plus 1 times 2 to the first power, plus 1 times 2 to the 0th power. Now, this is a neat thing about binary. The reason it's used in computers is because there's a lot of little tiny switches in the circuits at its core concept. We can represent that a switch is off if it's 0, and if it's 1, that represents that the switch is turned on. Well, the other neat thing is that 0 can also represent false, and 1 can represent true. Now we know that 1 times any number is the same number, and 0 times any number is 0. So we don't really even need to include these 1 times things. So if we simplify this now, we know that we have 4, because 2 times 2 is 4, plus 2 times 1, 2 by itself is just 2, and 2 to the 0th power is always just 1. So 4 plus 2 plus 1 is 7. This is the number 7 in binary. Now, what if we were to switch this to a 0? As I said before, that'd be the same as putting 0 times in there, which just means that it goes away. It's not involved in the process. And now we know that 4 plus 1, and that equals 5. So this is how to count in binary, how to figure out what a binary number is back in a decimal format that makes probably more sense to us than looking at a long chain of 1s and 0s. We also know now that 0s can represent false. They represent a switch being turned off. Later on, they will actually also be used, well, I guess this goes along with false and true. They're like a checkbox. If a checkbox is unchecked, then it is a 0. And if there's a little check mark in there, then it is a 1. So we can use this 1s and 0s, very simple, basic, to represent many different things, whether the state of switches, actual numbers, as we've covered here, and then also Boolean statements of true and false. Now, you might be thinking, I really would hate having to look at some really, really long number and figure out, how do I remember this? This is why we use hexadecimal. This is where the hexadecimal part comes back in again. So if we look at hexadecimal, one symbol is capable of representing all the way up to the number 15. And we just talked about representing binary numbers. So let's look at this number specifically. There's 4 ones that we have. What does this equal? Well, we know that it goes all the way up to here. So 8 plus 4 plus 2 plus 1. And this gives us the number 15. So in hexadecimal, this would be the letter F. Now, the neat thing about this is there is a name for this. It's called a nibble, sometimes spelled with an I, but since a byte is 8 bits, and a bit is binary digit, so since a byte is 8 of these guys, a nibble with a Y makes sense to me. That is only 4, because again, we spell the word byte like this with a Y in it. So I think it's kind of neat when we include a Y in nibble as well. This is definitely the formal spelling. If you go on the internet, this is sometimes spelled with an I, sometimes spelled with a Y. So it's personal preference, I guess, at that point. What this means, though, getting back on topic, is if we were to have the byte 111, 1111, this can be represented in hexadecimal as FF, because this nibble is an F and this nibble is an F. So let's take 1 away from this. What is this now? Well, again, 8 plus 4 gives us 12, plus 2 gives us 14, and then it's 0, so we don't add that 1 in there. That gives us the number 14, which we know is the letter E. So this would be represented as EF. Now, so on and so forth. This is the benefit of using hexadecimal. And that's why we use it here at our origin point, because the computer ultimately only understands ones and zeros. It needs to know what switches to turn on, what switches to turn off, what things are true, what things are false, and it does all this in binary. It has no concept outside of binary, in fact. So those little locker numbers that we were talking about, you would have locker number 0, locker number 1, locker number 10, locker number 111. Well, the address first starting out is a very, very large number, and we represent it in hexadecimal as hexadecimal 80,000. So there we go. We have talked about the system we're familiar with. We've talked about hexadecimal. We've talked about binary. We've talked about how these two relate to one another. We've covered counting. We've covered shortcuts for converting them back in the decimal so that it makes sense. Now, yes, in hexadecimal you can do the same thing. If you were to be greeted with a number like this, you could say that you know it's the same thing as 1 times 16 to the first power plus F, which is the number 15, times 16 to the 0th power. And if you were to type that into a calculator, it would spit out, well, let's see, 16 plus 15, it would spit out 31. So we would know that this is the number 31 then. So we can use this as well to convert hexadecimal numbers into easier to understand decimal numbers for ourselves. Alright, so the only thing I haven't talked about yet is this whole 64-bit thing. You've probably heard about 32-bit computers and 64-bit computers and wondered, why did we switch from 32 to 64? And the reason for that is RAM size. with 32-bit, that means that we can have 32 ones and zeros. We can have 32 of those little guys. Now, since we know that we can represent them as nibbles, 32 divided by 4 will give us the number 8. So in hexadecimal, that means the largest number we can have is 1, 2, 3, 4, 5, 6, 7, 8. This is the largest RAM address that you could possibly have. And if I remember off the top of my head, it's been a little while, I believe that is 4 gigabytes. You can't exceed 4 gigabytes of RAM when you have 32-bit. Now, modern day computers will have 16 gigs of RAM, 32 gigs of RAM. They'll have much, much more RAM. The reason for that is we have been slowly switching over to 64-bit, which means that the largest address or the largest numbered locker you can have is this one, which is an extraordinarily large number, a number that we'll probably never ever need to exceed. Granted, the people that wrote the Internet Protocol version 4 also didn't necessarily think at the time that we would exceed the IP4 addresses, and now we have IP6, so who knows, maybe someday we will exceed that, but probably not in my lifetime. So that is why, I should say, that is what we mean when we say that we're using 64-bit. So just to recap, we have 3 lines of code. But we've explained what they mean, and this is the framework to get started, to start to move forward. We know that we're using 64-bit. We know that it's 64-bit version 8 of ARM. We got this information from the specifications. And we also know that our program is starting at 80,000. It's going to end up there no matter what. That's where the bootloader is going to put it. It's kind of like if you were to say you wanted to book a flight to Paris, you know that you're going to land in Paris. That's not the way this process works. It's more like you get on an airplane and they give you a parachute with a map and throw you out of the airplane, and when you land, the map says you are here. And in this case, you are here at hexadecimal 80,000. So we haven't actually written any code to assemble, but we have the framework. And that's the beginning. I think that keeping you here for this period of time is long enough. And I do look forward to seeing you in the next video, and we will actually start doing code in the next video as well. So I hope you found this video educational and enjoyable, and we look forward in seeing you in the next video.